All right, welcome back. So the engine's completely disassembled, and now we're going to be more closely identifying each one of the components of this engine. We're going to go through the bottom end of the engine, so the short block, and work our way up through the valve train and then into the cylinder head. This video shouldn't take too long, but I never know how many stories I want to tell. So here we have in front of us the crankshaft. The front of the crankshaft is over in this direction. The back of the crankshaft's over here. So the transmission flex plate or flywheel actually bolts back here. So this is where all of our power goes out of the crankshaft to drive the vehicle. Now remember, some of the power actually goes out to the front because we have what's called the front end accessory drive. And that's going to drive the alternator, the water pump, the power steering pump, AC compressor, all that stuff. So our crankshaft has got a main center line, which is actually down through the center here. There's main journals we have from the back. We've got one here, a main journal down in here, a journal there we can see pretty clearly, that one, and then of course the front one. So this being a V8, we actually have 5 main bearing journals. And this is where the crankshaft actually spins. So it spins on those crankshaft main journal center lines. Now, when we look at this crankshaft, we see that these two journals here, you know, if we created a center line through them, then we have these journals over here. These are the rod journals. And as this spins, this one is going to orbit around this position. And whatever distance it takes from this position to 180 degrees over here out in space, that's the stroke of the engine. And that's that's the distance that the piston is going to sweep inside the cylinder. So the other components of this crankshaft, we have, like I said, we've got our main journals, our rod journals, and then we have these oil holes right here. These are drilled through the crankshaft. Now this journal right here not only has this bearing surface on this outer circumference, but there's actually a bearing surface on this side and then on this side. And the bearing is there to help control the front and back movement of the crankshaft. And this is the bearing from the disassembly video. This is our thrust bearing. It's going to sit just inside here. Oops. It's going to sit just inside there, and the crankshaft will be allowed to move back and forth just a little bit, usually about say 4 to 7 thousandths of an inch for most engines. And 4 to 7 thousandths of an inch is about, you know, the thickness of some thick paper to, you know, twice the thickness of thick paper. And that's how much they want this crankshaft to move back and forth. So other parts about it, of course, on the back side, I said we've got a series of bolts that are for the flex plate of the flywheel. There's also a sealing surface because we have what's called the rear main seal that seals all the oil and crankcase gases from leaking out of the back of the engine and making everything wet underneath the car. So the other part that we have that we worry about on these are these oil holes. So how do things get lubricated? Well, the main bearings, which are mounted in the block, they are connected to the oil galleries that I pointed out in a previous video. And the oil actually comes from the block because this actually sits down in the block. And the oil is actually pressurized and comes out through this hole here. It goes through this oil groove, and then actually it creates an oil film between the bearing surface and, the journal surface and the bearing surface. Now it's being pressurized in there, but we see this hole, and this hole is actually drilled through the crankshaft, and if we can see it go all the way through, we can see it poke out the bottom. So the way that the rod journals get oiled are through oil holes drilled through the crankshaft. So the main bearings get the lubrication from the block, and then the rod journals get lubrication from the main bearings. If you have an issue on either one of these bearings, let's say some trash gets in there and it causes the oil clearance to be too large and it loses too much oil there, then you will affect both bearings. So it's kind of like a cause and effect. So we have something go wrong here. Well, something could have gone wrong here first, and that's what we're going to look at. So this is the oil passage through here. Now each rod journal has its own. So we see that this one is actually coming out this side here, and then there's yet another hole for the other rod journal, and it's going to go down through and take its own path to the next main journal. Okay, so we see this is how it works. Now this journal and this journal, these mains here, they actually feed 2 rod journals, and then the end ones only feed 1 rod journal. So that's how that works. So the other parts of the crankshaft. So these large masses of steel right here, those are called the counterweights, and they're designed to be of a certain mass so that it counteracts the reciprocating action of the crankshaft rod journal, the connecting rod, and the pistons that are attached to this and this one here. So these are acting like a counterbalancing mass as the engine's running. You ever hear of somebody having the crankshaft balanced? They are going to affect the weight of these, or either going to make them heavier or make them lighter. And you'll see that whenever you take an engine apart, or even on this one here, from the factory, it's actually been drilled. So when they measure the imbalance of this crankshaft, they attach weights that mimic the weight of the pistons and the rods on each one of these rod journals, and they spin it. And if it's indicated that it's too heavy, then they'll actually drill the crankshaft counterweight. And they can drill it in any one of these positions, because you can see that we have a drilled hole there, and we've got a drilled hole there. On the back end, we've got 2 deep holes about 1/2 an inch, and then there's also a divot that's just been drilled partially. So the counterweights are going to be dependent on what piston and what rod assembly is going to be used in that engine. So yeah, on the front of this crankshaft we have our timing gear, and this is what's going to drive the timing chain, which is then going to drive the camshaft. This one here has this large spline section because that's what drives the oil pump, and of course we have our crankshaft dampener bolt out the front. Okay, so let's go ahead and bring up our next piece. Our next piece is going to be the camshaft. So here's the camshaft from our engine, and we see that it also has our 5 cam journals, and that's how it's going to be supported in the engine. And if you remember, these things right here are called the lobes. These are the cam lobes. We have one for intake and one for exhaust, and then I think on the other side will be intake and exhaust this way. But these are how the valves are going to be opening. Now, because I can't hold that one up at such a good angle, I've got a smaller camshaft right here, and this one, let me get this in focus. There we go. So you see this one here has got the same lobe design. It's not necessarily the same design, it's the same lobe shape. There we go. And it's got an egg shape to it. So the bottom of it here, that's where the valves are going to be closed. And then as this rolls around, the lifter is going to be pushed by the lobe itself. So I've got a lifter out here from our engine, and you kind of get the idea. As this camshaft is spinning, the lifter is going to go up the ramp. It's going to go to the very top of it, and that's the maximum amount of valve opening. And then as this continues around, the valve is then going to close. And that's what a camshaft is. Now this camshaft is damaged. It is not any good, because we can see that there's actually some heavy pitting right through here on the nose of this lobe. This is actually pretty common on these. And because of this, one of the lifters is also damaged. So you have, complementary damage. So this might have been what failed initially, but you got to think about the wheel that rolls over this from that lifter. That wheel is not going to like that section either, and it's going to get damaged too. So we're definitely going to need to install a camshaft and a new set of lifters in this engine. So the front of this camshaft has got a series of bolts. It's got a series of bolts for the cam gear. Let me point this out again just in case. So on this lobe for our camshaft, we can see it's got some pretty heavy pitting, and this pitting is what's going to cause this camshaft to not be usable. Let me see if I can get that in focus better. Right there, maybe. Yeah, maybe not. But this heavy pitting that's the camshaft's no good. Now, if this were a rare and expensive camshaft, it could be repaired by a cam shop. But because this is a GM LS or LQ or LM, it's a very cheap camshaft, so I probably have some laying around here. But we would have to replace the lifters at the same time, because the lifter that rolled over this section, you know, it's supposed to be rolling against a nice smooth surface, but this one, it's been hitting on that rough section, causing some heavy wear on the roller. Okay, so the next piece that we have out of our engine is our piston and rod assembly. We see that we have our connecting rod over here, our rod cap attached, and then the piston. Holding the two together is a wrist pin, and that's like a wrist on your hand, but that's a wrist pin. If you're over in England, it's called a gudgeon pin. But we have our piston, our wrist pin, our connecting rod, and our connecting rod cap. On the piston, we have our piston rings, and we see that there's actually 3 piston rings on this one. There's a piston, this lower one right here, this middle, and the top one. So it actually goes our top ring, our middle ring, and our third ring, sorry. Or sometimes people call them the top, the second, and the third ring. But these rings have purpose in the engine, and that's what's going to help seal the compression and combustion above the piston, and keep the oil keep oil below the piston. You can see that our piston has a wear pattern on it, and this is actually a very good wear pattern. It's, you know, when you think about this engine, I believe had over 200,000 miles, and we see the wear pattern that's on the piston. It's very symmetrically shaped. It kind of looks like a, I don't know, maybe a balloon shape, I don't know. But that means that this piston has been very well fitted to the cylinder, and it hasn't been abused any. Now, if you find some that have a specific wear pattern in them, okay, so about the wear pattern, if you pull the piston out of the engine and you see a wear pattern similar to this, or it'll be kind of just a nice oval, but it's very symmetrical, that means that these pieces are probably good. But if you pull one out of an engine, and 1 or 2 or, you know, any number of pistons, they've got a wear pattern that kind of looks like that. That means that the rod is bent. That means that the connecting rod is bent, and instead of that piston going straight up and down inside the cylinder, the rod has got a bend in it, which is causing this piston to sit sideways as it goes up and down inside the cylinder. So it should go up and down nice and straight like this, but if this rod has a bend which causes the piston to lean, then that wear pattern is then going to be worn into the piston, and you're going to be able to see it. And it's pretty much you know, a guarantee that if you have a wear pattern like this, a parallelogram if I remember right, then the rod is bent. So that's something that you got to look for. You know, those simple things like ringing the crankshaft, looking at the wear pattern on the pistons. So to look at pistons a little bit more closely, I've got some cleaner ones here. These are actually out of a Ford 5-liter Coyote. And I'm going to do a quick disassembly of this so that we can see the wrist pin actually coming out. So this piston here has got what's called a full floating pin, and that means that this pin that's inside here is not press fit to the piston or the connecting rod. So you have 2 types of wrist pins when it comes to cars. We have a full floating and a semi-floating, or sorry, we have a full floating wrist pin and a pressed fit wrist pin. So this one here is full floating, so it's got a little circlip that's holding it in there, a little wire retaining ring. Try and get it out. Try and get underneath it without stabbing myself. Try the other side. Might have better luck. There we go. So here's our circlip. It's just a little wire clip little wire clip. It's a round wire clip, usually about 60 thousandths of an inch thick. And inside there that we have our wrist pin. So let me try and push this pin out. Sometimes when you're messing with the groove that clip goes into, it makes it a little bit tight to get the wrist pin out. So let me try and force it out with this. There we go. So we can see that pin's coming out of the side of the piston, and we see that they're connected here. And if I continue on with it, I should be able to disconnect the connecting rod and the piston. All right, so we've got our connecting rod out, and we see the general shape of it. We have our small end and our big end. I know those are very technical names, but that's how they're named. Our small end and our big end. This end right here goes up to the piston. This one goes down to the crankshaft on the rod journal. This one here has a bushing pressed into it, and that's what provides the compliant surface for the wrist pin to slide on. So let me try and pull this wrist pin out the rest of the way. It's only tight, remember, because I probably dinged up the board that it goes into. So here's our wrist pin. This is probably the most precision component in the engine, because these are usually going to have a clearance fit between the pin and the rod, or the pin and the piston, that's going to be on the order of about 5/10 thousandths of an inch. So that's like 1/6 the thickness of a sheet of paper. So it's going to be a very, very precise fit between the wrist pin and the connecting rod. And we see that I can just slide this guy in here. Once it gets lined up, it goes right in and out. And again, this is a full floating wrist pin. So looking at the piston, I've already removed the piston rings on this one, just so we can see the ring grooves, but we have our oil control ring down here. Our next one up is going to be our second compression ring. Well, they say it's a compression ring. We'll just call it the middle ring. And then we have our top ring. Now this piston has another ring, or not necessarily a ring groove, it's actually called an accumulator. So that any gases that get past the top of the piston, past this top ring, they'll actually have a place to expand into. And instead of going down and then affecting the sealing of the second ring, it'll just give it a place to kind of accumulate. Now the piston rings on this engine, starting from the bottom, they have very specific purposes. And our bottom one, which is called the oil control ring, you could imagine is going to control the oil. So what it consists of are two pieces. In many cases, there are some one-piece oil control rings, but this here is a three-piece oil control ring. Our centerpiece is called the expander. You can see it has kind of a crinkle shape to it. Okay, let me see if I can get a little bit closer there. Okay, we can see it's got a bit of a crinkled shape to it, but this right here is an expansion type ring. So what its job is to do is to support these rings, and these are very thin rings. They're just stamped out of sheet metal. Well, I don't know, maybe they are, maybe they're rolled out of sheet metal, but they're very thin rings and they're very flexible, okay? These are called scuffers. So the scuffers are supported by the expander ring, and there's going to be a scuffer on the bottom of the ring, and then there's going to be a scuffer on the top of the ring. Now when this goes onto the piston, the assembled group here, the assembled set piece, is actually larger than the cylinder, because when you put it down into the cylinder is going to compress it, and that means that this ring, or these rings, are going to be pushing out against the cylinder wall. And you can imagine if I take one of these thin rings and I scrape it down across the cylinder wall with a bunch of oil on it, this is going to act just like a squeegee. So it's going to be an oil control ring for the cylinder. Now I'm going to jump to the top piston ring, because the top piston ring doesn't have a lot of geometry to it, and it has one very specific purpose. The top piston ring is usually just a barrel shape. So if you could imagine the shape, the side of a barrel, That's going to be to the face of this piston ring. So the part that rubs against the cylinder wall is usually going to be a barrel shape for the top piston ring on modern engines. Now on older engines, they could have just a square face on them, but a barrel face piston ring actually provides a lot of additional benefits for them. So this top piston ring goes into the top groove, and again, this one is also, as it sits right now, bigger than the cylinder it goes into. So you actually have to compress it to get it down into the engine. So you can see we can compress it, and ideally when this engine is running, that small gap there in the end, when the engine is cold, that gap is usually going to be about, say, 15 to 20 thousandths of an inch. And if you could just kind of go back to high school science class, but what happens to things when they get hot? They expand. Well, because this can't expand radially this way, it actually has to expand in this circumference direction. So that means that these two ends are actually going to come closer together the warmer the engine gets. And ideally, at operating temperature, these two ring faces will actually meet in the middle. Now, when it comes to higher performance engines, what they'll do is they'll actually increase this gap so that this piston ring can operate at a higher temperature, because the higher temperature means more expansion, and then they'll actually have it come close together. Now, if a piston ring is installed with insufficient gap, it will actually break the piston, because as this guy grows in the circumference, these two faces will actually meet up. Well, they can't grow anymore at that point. So instead of growing in the circumference here, they'll actually start to grow in this direction here. So it'll have a wave in it. And this is sitting inside a groove in the piston. It'll actually force that groove open and break the piston. So if you ever pull a piston out and you see that maybe it's a new engine, or maybe somebody put a turbo on it or up the boost on the turbocharger, the supercharger, and the piston ring lands, which is the sections in between the piston ring grooves, are broken, there's a good chance that those piston rings did not have enough of an end gap on them. So, and that's actually something that's pretty common on the, I think it's the 2017 and 18 and up Camaros. It happens when people want to put superchargers or turbochargers on them, or up the boost from the original one. So our second ring, the second ring has a very specific purpose, but it depends on what you read. But the second ring, which goes in the second groove of the piston, it has one purpose. Okay, if you read some places, they say it's got two. If you read in some other places or talk to other people, they're going to say, no, it's not two purposes, it's this other purpose. So the original idea of this second piston ring is that it's for compression and for oil control. But the thing is it doesn't do a lot of compression. It's only for oil control, and we can tell because of the shape of this piston ring. So we can see on one side of this piston ring, hopefully you can see it, there's actually a line machined around the outside of this. And that's actually a ledge. And it's a ledge that acts like a scraper. So the bottom of the piston ring is on this face here. So as this piston ring goes up, that ledge that's built into it is like a squeegee. So if we take a squeegee and we swipe it across the surface like this, it's not very effective. But if we swipe it back this way, that angle against the surface, okay, so if I say wiping a surface, let me put my screwdriver down here. So if I take a squeegee and I swipe it across a flat surface like that, I'll pick up something, yeah, that's true. But what if I put that squeegee backwards? That squeegee is actually going to scrape the liquid off of the surface, and that's how this second piston ring works. And this type of piston ring is usually referred to as a Napier piston ring. And this part right here is only for oil control. And really by design, if any compression gets to this piston ring, that compression will actually push the piston ring back into the groove, and that compression will leak straight past the second ring. So the top ring, 100% of its job is for compression. The second ring, we might say 95% of its job is oil, 5 is compression. And of course, the oil control ring, 100% of its job is for oil control. So there's our piston rings and our piston. Oh, something else that I forgot to mention. I've been looking at it. But we see these piston rings are directional. And if you ever see a dot, hopefully you can see there's a dot there. Or if the name brand of the piston ring is etched on one side, that is up. It's always up. If it's a dot, if it's letters, if it's numbers, those will always go to the top of the piston when you install it. So if we look at our top ring has it too. It's got a dot right here. And that dot tells you that this piston ring goes up. If you put it in upside down, you will cause problems. Now with the compression ring, not so much. But with the oil control ring, if you put this in upside down, this engine will consume oil. All right, so now we're on to our next piece, which is going to be the main cap. Remember, this is a 6-bolt main cap. We've got 2 bolts here, 2 bolts here, and then there's 2 bolts that go on the sides of the main cap. And we have our bearing shell. Now remember, there are really 3 different types of bearing shells in this engine here. In some engines there'll only be 2 different types of main bearing shells. But this one here has got these 2 types of shells. Now remember, because it's got a hole in it, that hole right there tells you this side is going to go into the block in most cases, because the oil galleries are located in the engine block. And the oil needs to come out of this hole to lubricate this section here. And we see that this bearing shell doesn't have any holes at all. They do design the bearing shells so that it kind of idiot-proofs it to where you cannot install this bearing shell in the wrong spot, and you can't install this one in the wrong spot. Because if we see that the bearings itself, or the bearing cap, it has in it a notch machined into it here and a notch machined into it over there. And we see on our bearings they have a tang, and this tang is for assembly only. It's not to hold the bearing in place while the engine's running, it's only for assembly, because this bearing shell needs to be installed in the correct position, say front to back, okay? So it needs to be installed in the correct position. But we see that if I try to install this bearing, we have our tang, which is not lining up with the notch. We think, well, there's a tang over here. Well, let's just swap this bearing around. And you see, it still doesn't work. And that's why I say it's kind of idiot-proofed, because I've seen people do some silly things and they still installed the bearing with the tang in the wrong spot, or they have ground the tang off for some reason. So we can see that that bearing shell can't go in, but this one will definitely go into the cap, okay? And we see that that tang is lined up with that notch, and the bearing is positioned front to back properly. So other things about these bearings is that if we were to measure the distance from here to here, okay, from here to here, and then measure where it sits in the cap, this bearing is actually wider than the cap. And the reason for that, well, what that's called is bearing spread. The reason for it is for positioning and to get this bearing to lay properly into this main cap. Because while this bearing doesn't technically rub against the crankshaft all the time, it does have oil in there. And the shearing action of the crankshaft spinning with oil in between it and the bearing shell does create heat. And that heat needs to get out of the bearing area. And the best way to do that is through the contact on the back of the bearing. Because the bearing is touching the cap or the bearing is touching the block, it's going to be able to get rid of that heat. So that's our bearing shells. Now the rod bearings are very similar, they're just smaller. So we can see that the rod bearing is just a smaller diameter. It has the same thing. It's got the bearing tang on it. Now, not every engine manufactured out there has tangs. BMW and Ford both have gone without using them for some period of time, and then they've gone back to using them. but we see that the bearing design is pretty much the same. Now the different types of bearings that are out there, the most common ones are called tri-metal, and that's where it's going to have a steel backing, a copper layer, and then a lead layer. And then you're going to have bimetal, which is going to be a steel backing with an aluminum layer. And I believe these are actually a bimetal. Yeah, these are a bimetal bearing because this is definitely aluminum on the surface. The other parts of this bearing is whenever these two bearing shells are put together in the assembly, just like this, you would think it makes a perfect circle, but it actually doesn't. To measure from here to here, which would be 90 degrees from these parting lines, this distance would be smaller than if we were to measure from the parting lines here while it's assembled in the block. And the reason for that is something called oil wedge. You should be able to see this little bit of a light aberration right there, is that this part right here never touched the crankshaft or never even got close to it. The reason is that this surface here, this piece of the bearing is actually thinner from here to here when compared to here to here. And that thickness or that thinness is what helps oil to get wedged in between the bearing and the journal as the engine's running. The next piece from our engine puzzle is the crankshaft dampener. We kind of saw this one when it was being removed from the engine. And the way that this thing works is that it's actually got two metal masses that are connected by rubber. So this center section here is bolted to the front of the crankshaft. The crankshaft it's actually pressed into this hole. This hole is smaller than the snout of the crankshaft that gets put into it. And this part right here is driven directly by the crankshaft. And that part ends right here because on the outside of that inner ring is a rubber ring. And let me go ahead and color this. So that colored section all the way around is a vulcanized rubber ring where the inner ring and this outer ring are actually suspended separately. So if you could imagine an engine that's running does not run smoothly. It operates in pulsations. So if we have a V8 engine, every 90 degrees of this dampener's rotation, it gets a pulse from the engine. And that's because we have a compression, then that power stroke is what causes the engine to keep running. Those pulsations aren't necessarily, desirable, especially if we're trying to drive things smoothly, such as AC compressors, alternators, power steering pumps, and water pumps. So what they try to do is to smooth out the power pulses. The other thing is that yes, it does affect the front end accessory drive stuff, but this right here actually helps to smooth out the engine operation. So whenever this piece right here, let's say it's going clockwise, gets a power pulse, it's going to get a pulse to this side here clockwise. This guy's not going to react right away. It's going to be a dampener, so it's going to lag behind slightly and then slowly catch up as this rubber then starts to go from distortion back to its natural position. And it's basically acting like a spring on the suspension system. It's going to help to reduce the pulsations from the engine. Now, things to look at whenever you pull off crankshaft dampeners is you've got to look at this rubber ring inside there. If it's cracked or if it's missing, any pieces or chunks have come out of it, the dampener has to be replaced. You can't install that thing back on the engine because you got to think about what the crankshaft dampener does. The crankshaft dampener drives all the accessories on the front of the engine. It could drive the water pump. And if this ring were to stop spinning because the rubber is gone, then you're not driving your water pump, you're not driving the alternator, you're not driving the power steering pump. And I've seen it before where the rubber has slipped out entirely and the engine's making a ringing sound, and what that is this inner ring is trying to drive the outer ring just by rubbing on it. And that's not going to work very well. So when you're inspecting an engine to do any major repairs, let's say you have to take it apart partially to do an internal repair, do a quick visual inspection to make sure that rubber ring is okay. Make sure it's not chunked out, and make sure it's all in place or not slipping out. All right, so the next piece that we've got is another big one, and this is our cylinder head. Now this is the dirty cylinder head off of our engine. We're not going to be able to see all of it, we're just going to see a portion of it here. So here's our dirty old cylinder head. And let's talk about the parts of this cylinder head. So our spark plug is what pokes through this hole here. Okay, so that's where our spark plug goes. And this is the combustion chamber. So combustion chamber, spark plug hole, and then we have these two valves. So the small one is the exhaust valve, the large one is the intake valve. And they're inside the combustion chamber, and then the piston goes up and down on these. So we have, we've got our 4 chambers, our 1, 2, 3, and 4 chambers. We've got 4 intake valves, and we've got 4 exhaust valves on the cylinder head. Now there's other parts in the cylinder head, and there are still other designs of cylinder heads. So what I'm bringing over is a cylinder head you've seen before if you've seen the other videos. And this one is a different type of cylinder head because it's got a different count of valves in the combustion chamber. So the engine that we're working on is a 2-valve cylinder head, overhead valve engine, and then we have this one, which is a single overhead cam, but it's a 4-valve engine. So in the background we can see that we've got intake exhaust for 1 chamber, and then we have on this cylinder head here, we've got 2 intakes and 2 exhausts. There's different reasons for doing that, and we could go into that, but one of the reasons is that if valve train packaging is a lot easier to do, especially if you want to do overhead cam. And if we have a small displacement engine, we need to be able to get a lot of air in and out, and it's usually going to be a higher RPM engine. And if we have 2 valves placed like this, as the air comes into the cylinder, it's actually going to do a tumbling action, and supposedly that tumbling action is better for higher RPM power output, as opposed to our 2-valve cylinder head, where we have, instead of a tumbling action, the air is going to be shot down through the intake port, which is over here. Oh, wait, hold on. There's our intake port. The air comes in right here, and you see it kind of comes at an angle. It goes to this valve, and as this valve opens, the air actually comes and swirls in. And they say that swirling is what allows for more low-end torque and more low-end power, meaning lower RPM response. So if you can think about, what are Hondas known for? Well, they're known for revving up really high, having horsepower but not a lot of torque. Or Chevy V8's known for? Well, they're known for having a lot of torque and horsepower, but not a lot of RPM, horsepower, or torque. They kind of run out of RPM unless they're built a certain way. So the next thing that we've got are pieces that we've seen before. We have our push rod here. We have our rocker, and I'm going to bring the lifter back out. There he is. And if we put these pieces together, let me try and put them together like that. And we put a camshaft out on the side, and we're going to bring in our little Subaru camshaft. And this isn't the angle that everything happens at. It's going to happen at an angle kind of like this, but it's just kind of hard to demonstrate. So I'm just going to lay it down so that we kind of see it working this way. So as this camshaft is spinning, the lifter is running against it. And as this lifter runs against this camshaft, we can see that we get to this nose section of the cam lobe, and we can imagine that this lifter is going to be pushed away from the camshaft. As it gets pushed away, it then pushes up on the push rod. And as we've talked about before, it pushes up against the push rod, which then pushes on the rocker arm. And this rocker arm just rocks back and forth. And we have the valve on this side, and the valve is then going to be opened by the rocker. So just like this here. This is pretty much the layout of this LS engine. Of course, it's not exactly the right valve. That's a Subaru valve. And so that's what we're looking at there on the valve train. And we're going to do more discussion about valve valve train in general and the different designs of valve train. But that was just another redo of what we tried to do on the table during disassembly. Okay, so we've gone through most of the parts of the engine. We talked about the crankshaft, the main journals, the rod journals. We talked about the connecting rod and the wrist pin. Talked about the pistons. So we've got our piston here. We've talked in general about our pistons. We'll get more specific as we get to ordering parts. We talked about the piston rings. You know, the piston rings, we've got our 3 piston rings. We've got our top. We've got our second ring. And then we have our oil control ring. Those are all located on the piston. We've got our camshaft that we spoke about. And our crankshaft dampener. And then our bearings. And we talked about where this one goes. That one's going to go into the block in most cases. This one here is used to control thrust movement of the crankshaft. And we have our rod bearings. And the rod bearings, just like main bearings, are oftentimes going to have these little tangs right there on the end of them. And those tangs are going to help position the bearing. And once it's in, the tang doesn't get used anymore. And we talked about the cylinder head, 2 valves per chamber, then 4 valves per chamber. So that's everything. We'll get in more detail as we go through further inspection and measurements and machining and cleaning. But this is just a high-level overview of the components of the engine. Now we do have the cylinder block, but we're going to get more in that, and that's just, didn't want to try to fit that all in the picture here. So we'll have a video all about that, and it'll be part of the engine machining or engine block machining video. So until next time, I'll see you later.